Alright, welcome back. I'm going to talk about the theorem, uh, the several theorems in singular value decompositions. This video is part of the singular value decomposition, the lecture video series. So first, we're going to see theorem 2. Let A be m by n matrix, and the matrix is A transpose A, and A times A transpose are symmetric. So let's prove this statement. To prove this, we start from the transpose of A transpose A. Then we can say this is A that is equal to A transpose and transpose. Is that right? So because the transpose and transpose is will be cancel them out, right? So we can say this is equal. Then this is nothing but A transpose A. So A transpose A is equal to A transpose, right? And then next one is this A transpose and transpose. Okay. So A transpose is that's gonna be A transpose and transpose, right? So but those transposes will be cancel them out. So we got A transpose. The proof is done. And the second statement, the null of A, and this nullity, right? Nullity of A is equal to nullity of A transpose A. So it means that the number of the element, number of solution of the matrix AX equals B is equal to the number of solution of the matrix equation A transpose AX equals 0. Okay, that's the meaning of this. So we choose the non-zero vector V. That is a solution of the matrix equation AX equals 0. Okay. Now we the left multiplication of A on the both sides. So we got A transpose A vector V. And the right hand side going to be just zero vector, even though we apply the left multiplication of matrix A on the, of the A transpose on the right hand side. So then A transpose A and vector V is equal to, because associative property of the matrix multiplication is satisfied. So A transpose of A times vector V, we can compute the A times vector V, but A times vector V is what? Vector V, right? I mean 0, sorry, 0 vector, right? So now then, because we're going to get the A transpose and 0 vector that is equal to 0 vector. Okay, so we start from the we pick the arbitrary solution factor of the AX equals 0, which means that we pick the arbitrary element of the null space of matrix A, and then that one is also the element of the null space of A transpose A. So it means that the nullity of A must be less than or equals nullity of A transpose A. In other words, we can say nullity of A transpose A must be greater than or equals nullity of A. That's what we have proved here. And now we're gonna pick the solution vector of the matrix equation A transpose A of x equals 0 vector. So we pick the solution vector, which means a non-zero solution vector. That's a non-trivial solution vector, such that A transpose A vector V equals 0, and we multiply V vector V transpose the left hand side, and that's going to be AV vector AV transpose and AV, right? That's the square of the L2 norm, because here L2 discrete L2 norm working as just 2 norm. Okay, that's the vector U. 2 norm of vector U is the square root of the dot product of vector U. Okay, so we can say U transpose U. Okay, so So this is equal to the square of L2 norm. Okay, that must be greater than or equal to 0. Okay, so but that is equal to V transpose 0 because 0 vector, because we multiply V transpose on the left hand side for each term, each side. So we got this, but that must be greater than or equal to 0, right? And then the right hand side turns out to be 0. It means that A times vector V must be 0 vector. Okay, so it means that the nullity of A transpose A must be less than or equals nullity of A, because we choose arbitrarily, we pick the vector solution vector V from the A nullity of A transpose A, null space of A transpose A, and then it turns out that that solution vector is the solution vector of the AX equals 0 vector, right? So nullity of A transpose A must be less than or equals this. Okay, so we proved this and that because of those two inequalities. So it turns out the nullity of A must be equal to nullity of A transpose A. It means the number of the solution vector of the AX equals 0 must be equal to number of solution vector of the matrix equation A transpose A X equals 0. Okay. Third statement: the rank of A is equal to rank of A transpose A. The It means that what the number of the pivot column is equal to number of A is equal to number of pivot column in A transpose A, and then there are a lot of the equivalent statement. But please the for the rank, please watch the video of the matrix inverse matrix. Okay, so see, okay, the since the we in the previous statement we proved that nullity of A is equal to nullity of A transpose A. So then actually rank of A plus nullity of A, it must be equal to the n. Here the n is the number of column in matrix A. Okay, so then we can say that rank of A is equal to n minus nullity of A. Okay, so keep in mind this rank of A plus nullity of A must be equal to the number of column in matrix A. Okay, so because that, you can say that, and then that nullity of A, we just proved that nullity of A is nothing but nullity of A transpose A. Okay, and then that must be equal to what, rank of A transpose, right? So proof is done. So here this is equal to rank of A transpose A. It was typo. Okay, so let's see the next statement. The eigenvalues of A transpose A and A times A transpose are real and non-negative. Okay, so to prove this, we need to prove the correlate one, and to prove this, we need to prove theorem 3. Okay, so it's going to be just main. That's the main the part of this video. Okay, just take a look at it. So suppose A is corollary 1. Suppose A is a symmetric n by n matrix, then there exist n eigenvalues of matrix A, and such that n eigenvectors form an orthonormal set, and then n eigenvalues are real numbers. Okay, so we're gonna prove this, and then we replace the A by A transpose A and A transpose, because A transpose A and A times A transpose are symmetric, right? So we just proved that. So if this is true, then these two guys have the n eigenvalues, which are real numbers. Okay, and then in addition, the n eigenvectors corresponding to those eigenvalues are orthonormals each other. Okay, so we're going to prove this, and then by corollary 1, the eigenvalues two matrices, actually symmetry matrix, right? Two eigenvalues two matrices are real. Okay, and then I'm going to prove the negative. Okay, so to prove the corollary 1, we need to take a look at theorem 3. Okay, so theorem 3 says that the n by n matrix A is symmetric if and only if there exists a diagonal matrix D and an orthogonal matrix Q with A can be expressed as QDQ transpose. Okay, so why? Because okay, so let's prove this one. Um, Suppose that there exists diagonal matrix D and an orthogonal matrix Q with A is QDQ transpose implies A is symmetry. Okay, so all what you're gonna have to do in here, this direction, we need to prove that A is symmetry, but we assume that there exists diagonal matrix and an orthogonal matrix Q, so that A can be factorized as QDQ transpose. All right, suppose A is a QDQ transpose, and the Q is orthogonal, and the D is a diagonal matrix. Then A transpose, we're gonna take a transpose that equation. So A transpose that relation, okay. So A transpose equals QDQ transpose and transpose, and then this is gonna be Q transpose transpose and D transpose and Q transpose. So transpose is just cancel them out. So we got Q, nothing gonna happen, change. And then D transpose, since D is a diagonal matrix, a transpose will not effect on D. So we just get D. Okay, so QDQ transpose, that's going to be A. So we see that A transpose equals A. So A is symmetry, we can say that, right? Okay, proof is done. The next implies, so that implies, so let's say A is symmetry, and then we're going to prove that, we need to prove that implies there exists a diagonal matrix D and an orthogonal matrix Q, and A is QDQ transpose. Okay, so we're going to claim that for any symmetry matrix A, and the A can be written in the form A is equal to QDQ transpose. Okay, so the first one, let's say the lambda 1, lambda 2 are distinct eigenvalues of matrix A. So it means that AV1 and lambda V1 V1 and AV2 is lambda 2 V2. Okay, it's definitely lambda V1 V2 are, I mean, eigenvectors. I mean n by 1 eigenvectors. Okay, so then since the what here we assume that A is a matrix symmetric, right? So since A is A transpose, so we have lambda 1 minus lambda 2 times V1 transpose V2. Okay, we're gonna start from this one. Right? So we definitely show that this one turns out to be 0. Okay, so it means that V1 transpose V2 equals 0, must be 0. Why? Because lambda 1, lambda 2 are not the same value. Okay, I mean lambda 1, lambda 2 are distinct eigenvalue. That's our assumption, right? So we pick the two eigenvalue, distinct eigenvalue. So V1 transpose V2 must be 0. Okay, so it means that what V1, V2 must be orthogonal eigenvectors, right? So okay, you see why this is turns out to be 0, because we're gonna distribute lambda 1 and lambda 2, so we're gonna get this, right? So but lambda 1 v1 is what a v1, we can say that because the lambda 1 is eigenvalue of the eigenvalue corresponding to eigenvector v1, so that must be equal to a v1. And here lambda to v2, we can say this is the a v2, right? Okay, so then here transpose, we do transpose a v1, we're gonna get v1 transpose and a transpose v2, and then the right hand side, I mean second term, just write it down, just copy it here. Then we got this. These two terms is identical, right? So it turns out to be 0. Okay. So I told you, since the lambda 1 is not equal to lambda 2, then v1 transpose v2 must be 0. So it means that v1 and v2 are orthogonal eigenvectors. So whenever we pick a pair of the eigenvalues, lambda I and lambda I and lambda j, then we can construct the orthonormal vectors, actually orthonormal eigenvectors, right? Dividing by its norm, okay, its magnitude. Okay, so what if two eigenvalues are identical? Okay, if two eigenvalues are equal, then still it's okay. We can construct the orthonormal vectors using Gram-Schmidt process. So what is it? Gram-Schmidt process? Please watch the Gram-Schmidt process video, lecture video. Okay. So now from here, so see that now we prove that M by matrix A is symmetric if and only if, equivalent, there exists diagonal matrix D, orthogonal matrix Q. Actually, Q is the uh, the orthonormal or orthogonal eigenvectors. Eigenvector columns of orthogonal matrix Q is orthogonal, or you can construct the orthonormal eigenvectors. Okay, and then D is diagonals are actually what the eigenvalues of matrix A. Okay, so so by theorem 3, then there exists orthonormal matrix Q. Okay, so yeah, in the theorem 3 state that there exists orthogonal matrix Q, but in the proof of the theorem 3, we saw that we can construct the orthonormal vectors, right, by dividing each eigenvectors by each norm, L2 norm, right? So that's why we can say there exists the orthogonal matrix Q and the diagonal matrix D. Okay, now I told you the columns of Q are actually eigenvectors, orthonormal eigenvectors, and then the diagonal entries are actually the eigenvalues, right? Such that A is equal to Q dQ transpose by theorem 3. So that since Q is an orthogonal matrix, so Q transpose is equal to Q inverse of Q. Okay, keep in mind this. If a matrix is orthogonal, then its transpose is equal to its inverse. Okay. So now we do right multiplication of the Q transpose. That's not me Q inverse on both sides. Then we got this AQ equals QD. Okay. So I told you if we say that Q is the V1 through the Vn, express this one as column vectors, then Vi must be what? Ith column vector. Vi is actually what? Eigenvectors of matrix A. Okay, orthonormal eigenvectors. And then then a Q can be expressed as a V1 through the AVN. The QD, since D is a diagonal matrix, so QD is nothing but D11 V1 through the DN VN. Okay, so that means that AVI is equal to DII VI, and then VI is what I told you, eigenvectors of matrix A corresponding to eigenvalue DII. Okay, so now the multiplying this equation on the left by VI transpose give this. And then what VI, I told you VI is what? Orthonormal eigenvectors. So VI transpose VI must be 1. Okay. So DII, diagonal entry, is nothing but what? Is equal to VI transpose AVI. Now we show that eigenvalues of A transpose and A transpose A are non-negative. Okay, to prove this one, yeah, we express DII as like this. Okay, so now, this way. So here we're going to replace A by A times A transpose. Okay, so keep in mind this is what? Nothing but DII, which is the eigenvalues of A times A transpose. Okay, so replacing A by A transpose, we got this one. And then VI transpose A is nothing but A transpose VI transpose, right? So let's figure out the size of each the matrix. So this is n by 1, this is 1 by n, right? So that means what? We're gonna get the saying this is a WI column vector WI. This is also WI transpose. Okay. So here 1 by n means the including the transpose. When we transpose this one, we're gonna get 1 by n. Okay. So that means this is dot product, right? Which means the square of the L2 num of WI. Since there is square, that must be greater than or equal to 0. DII is what? Eigenvalues turns out to be greater than or equal to 0. Similarly, we can show that DII, which is the eigenvalue of the A transpose A, is greater than or equal to 0. Okay, so this proof is done. So from here, I proved that what? That statement, the eigenvalues are real and non-negative. To show that eigenvalues A transpose A and A transpose are real, I proved the corollary 1. See that? And eigenvalue is a real number. I proved the corollary 1. To prove corollary 1, I proved the theorem 3. Okay, and then to prove the eigenvalues of A transpose A and A transpose non-negative, I use the this one from here using the theorem 3 and expressing the diagonal entry in terms as like this, and then replacing A by A transpose and A transpose A. So I proved that eigenvalues of these two guys are non-negative. Okay, all right, that's for today.